Hello, everyone. Welcome to the Spectral Geometry in the Cloud seminar. Today, we have the pleasure of having Clara Aldana from Universidad del Norte. She will speak about quasi-isospectral potentials. The stage is yours, Clara.
Thank you, Alexander, and thank you, everyone, for being in this talk, and thanks for the invitation. So yes, I will talk about quasi-isospectral potential. So this is I wanted to work on, and at the moment I still have more questions than answers of what I had. So, but I want to tell you a little bit about it and how I got into this problem. So this is why it's still in progress, because we still have many questions, and this is with Camilo Andres Perez Triana, who started recently his PhD at Universidad de los Andes in Bogota. And as an overview, how this talk is organized, I will first talk about isospectral problem in differential geometry, a little bit. Then I will talk about isospectral Sturm-Liouville operators and on a finite interval and what is known about it. That is also quite a lot. And I will talk about isospectral potentials, the results, and now then about quasi-isospectrality. So I start by the beginning. At the very beginning, we have a compact manifold, a Riemannian metric in there that we denote as usual by Gij, and the Laplace operator of functions associated to it. That is the relation with the metric, and the second derivatives. And then if we assume that M is closed, we have the Laplace operator is essentially self-adjoint. We have a unique self-adjoint extension, and we can consider the eigenvalue problem with that is closed. And now this has some solutions, some solutions for functions that are not zero, as we all know here in this seminar. So the spectrum consists of a sequence of numbers that goes to infinity. Okay, so I have two examples that are very simple, also probably known to everyone, but let me just mention them. So if we have the string, that is the interval 0, 1, and we have the Laplacian on the string, and with Dirichlet boundary conditions at 0 and at 1, then we have that the solutions are given by the sign of n pi t, and the eigenvalues are n squared pi squared for n bigger than 1, greater or equal to 1. So the spectrum is n squared pi squared. It's simple because we only have an eigenfunction, and 0 is not part of the spectrum. On the contrary, if we have Neumann boundary conditions, so we have the conditions on the derivative of the function to vanish at the boundary of the interval. So the solutions are given in terms of cosine functions, cosine of n pi t. The eigenvalues are n squared pi squared, but this time we start in n equals 0. So this is the spectrum. So the difference between these two spectrums is only the eigenvalue 0. So now, so the isospectral problem for compact manifolds, we say that two manifolds are isospectral if the spectrum of the associated Laplacian operators are the same, including the multiplicities. So we know that isometric metrics are isospectral, and the question is whether isospectral are isospectral metrics also isometric. So if the spectrum of the Laplace operators are the same, including the multiplicities, where there is an isometry between the manifolds. So we also know that this answer is negative. There are counterexamples. First counterexamples were given by Milnor, Sunada, Vinegas. And but in spite of that, we know that on surfaces the spectrum determines the area and the genus, and in general it determines the volume. So for planar domains, the problem is very, very classical. So we have a compact smooth domain in the plane. There is the Dirichlet Laplacian, and then the question goes back to Vers and Kak when they ask where we can hear the shape of a drum. And some of the answers were, as we know, they are not. So But Gordon, Webb, and Wolpert, they constructed a domain in the plane. This is for planar domain. That is isospectral but not isometric, and this uses a transplantation method that is based on Sunada's method. I will show you the domain now. And well, there are also other results that are here. Like user convey Doyle similar when they construct also some other planar isospectral domains, and Seldish prove that analytic bounded domains with C2 symmetry are determined by the spectrum. So result. So the methods here are use heat equation with equation transform. So this is the domain by Gordon Welbert that they built. So these domains, this one here on the left and the one on the right, they are not isometric, so there is no isometry of the plane that takes one into the other, but they are isospectral, and that's proof using this transplantation method. So about isospectral surfaces, when one considers negative curvature. So we have this result by McKean that goes back to 72, when he considers compact hyperbolic surfaces, and then he proved that spectrum, the surface is determined by the spectrum. And that result was extended by Mueller in 92 to hyperbolic surfaces of finite area using well, several techniques like the construction of the surface. And then, so Guillemin and Castan proved compactness of surfaces of negative curvature. Everywhere, the curvature has to be negative everywhere, and then they prove that they don't admit like not trivial continuous isospectral deformations. So these are important results. And so for dimension 2, so we know if the curvature is constant everywhere, so there are only finitely many isospectral surfaces. But in general, what we know is that this set of isospectral metrics on a closed surface is compact, and this was proved by Osgood, Phillips, and Sarnak. And this is compact in the Smith topology of the set of metrics, and this is of course up to isometries. So this gives like an answer of how big this set can be. And what they use here to prove this result of compactness of isospectral metrics in dimension 2 is Sobolev-Benedict and Reddish lemma, heat invariance, determinants of Laplacians, and a Polyakov formula for the determinant. So I will explain a little bit about this because there are techniques. So let me start with the heat equation and the heat invariance. So when one has a compact Riemannian manifold, one has associated the heat operator. This is the operator that gives the solutions to the heat equation. So here we have the heat equation. We have an initial condition, and we have the boundary condition. So this is with the Dirichlet boundary conditions again. And we know that this operator has a heat curve. So the solutions can be written as integrals against the heat curve. Since we are in a compact manifold, we have that this operator is trace class, and then the trace is given. So the trace of the operator is just the sum of this function of the eigenvalues, and is given also by the integral over the manifold of the heat kernel restricted to the diameter. So what we have of all this, that is clear. So here, this is completely determined by the spectrum, the heat trace. So we know that the spectrum determines the heat trace. And if we have two isospectral metrics, then they have the same heat trace. And it's actually proof that if we know that they have the same heat trace for all values of t, then we have also that they have the same spectrum. So for the heat trace, and as we know also that as t goes to 0, the heat trace has an expansion. This is for dimension 2. This trace here diverges as t goes to 0. This is clear from this equation. As t goes to 0, this goes to infinity, but it goes to infinity in this form, with here a power of T2 minus 1 in front, and these are these coefficients, and these coefficients are the heat invariance that integrals over the manifold of some polygons that have geometric information. So they depend on the metric and its derivatives. And as t goes to infinity, the trace of the kernel goes to the dimension of the kernel of the Flash. So this is also very well understood and also has been studied very much. And we know that, as I mentioned before, for 2 dimensions, the first heat coefficient, what I didn't say before, but I said the heat trace determines the area and the other characteristics. So these are coefficients. Any question until now? Okay, so this is the first part I said, and then there are the Sobolev embeddings that I include here, and so I think maybe most of you are very familiar with them. But so this is the case for L2, the Sobolev spaces WK2. So K generalized derivatives in L2. So the embedding says that this HK of omega, when this is a Lipschitz a domain with Lipschitz continuous boundary in Rn, this embeds in LQ. This is if 2k is smaller than n, and this is for q smaller than 2n divided n minus 2k. So k is the number of derivatives. 2 here, this comes from the L2, and then this is compactly embedded when we have here this strict inequality. If we have here an equal, then it's continuously embedded. And the same here for this condition. So this Sobolev space is compactly embedded in Cm beta, where beta satisfies this condition, and this is it has to be greater or equal to 0. So these are the Sobolev embeddings, and that are used to prove compactness. So to use this Sobolev embeddings to prove compactness of this is like the strategy of the theorem of Osgood, Phillips, and Sarnak, or part of it is what I want to mention, is that the heat invariance of isospectral metrics are the same, and that the heat invariance are integrals over the manifold of polynomials that will involve the metric and its derivative, but in this case, they will work with the conformal factors. So we will have the conformal factors and derivatives of the conformal factors. So using that the heat invariants are the same, so they have these integrals, they are the same, they can obtain uniform estimates on the HK norms of the conformal factors. And then this, using the heat invariance, they have that for k greater or equal to 2. And this is actually a bootstrapping argument, so they used the previous one, that's the next one, that was first used by Richard Melrose. And then, well, for the first found in H1, they use the determinant of the Laplacian, and they also use some Manford compactification theorem for obtaining subsequence in moduli space. What I wanted to emphasize here is the part of the heat invariance and how that is used to obtain compactness. So some analogous compactness results for more general manifolds and in dimension 2. So one was by Osgood, Phillips, and Sarnak about so isospectral surfaces with the smooth boundary, they are also compact. Also for planar domains with finite connectivity and a smooth boundary, also by Osgood, Phillips, and Sarnak. And in higher dimensions, there are also results about isospectral metrics using the conformal Laplacian by Chang, Kim, Branson, Gilkey, Yang. There is also some compactness result by Müller and Benlen with Keller manifolds and using some functional related to analytic torsion. And this is also an important result. So when one goes from non-compact, from compact to non-compact, one has to leave the spectrum of the Laplace operator and talk about the resonance set to address these problems. So it could be the resonances, it could be the phase, the scattering phase, or the scattering matrix, depends on different things. So it's also a very extensive theory. But what Broadwick and Perry and Perry proved was that isoresonant conformally compact surfaces that are hyperbolic near infinity, they are compact in the smooth topology, and they also have other results for higher dimensions. And I also proved some compactness of isoresonant surfaces with asymptotically hyperbolic clasp with some extra conditions. And me together with Pierre Alban and Frédéric Rochon also proved some relatively isospectral surfaces, compactness of relatively isospectral surfaces with clasp and funnels. And for that, we use renormalized determinants. And this is a concept for relatively isospectral that we introduce in order to prove that using the trace of the difference of the heat operators. Okay, now I go to talk about Schrödinger operators on compact manifolds. So we have a compact Riemannian manifold, we have the Laplace operator, we have a potential. So this is usually a function that is smooth on the manifold, but one can also consider potentials are in LP, usually we consider L2, but one can also have some results for LP. And we consider the operator Laplace plus potential. So one has to fix a domain if there is no domain given, or if M has a boundary, one also has to fix a domain. And fixing the domain, we fix the closed extension, and then we have we can look at the eigenvalues of this problem that are again solutions to this eigenvalue problem. And we have that the resolvent is compact and the spectrum is discrete. So we have the same case as for a compact manifold. And we can define isospectrality of potentials. So we have two potentials are isospectral if the spectrum of the corresponding Schrödinger operators, this is Laplace plus potential, are the same, including multiplicities. So what we know is similar to the case of the manifold. If we have isometric metrics, that the spectrum is the same. Now we have here the Laplacian is the same, but if we have an isometry of the manifold and we know that one of the potentials is the other one, but decomposed by this isometry, then they will have the same spectrum. And so the question that comes here is the same as it came before, where we have isospectral potentials where they are related through an isometry of the manifold. And again, the answer is general, is negative in general. So the spectrum does not determine the potential. But however, there are positive results. And we also would like to know what geometric or topological quantities can this spectrum of the Schrödinger operator determine. So for the case of an closed interval, the string that I mentioned before, 0, 1, if we have a smooth potential that is positive, in order to have a closed self-adjoint extension, one has to choose boundary conditions. And some of the boundary conditions that we choose for these cases will be either Dirichlet, that is vanishing at the boundary of the interval, Neumann, that is when the first derivative vanishes at the boundary of the interval, Robin, that is this condition, u prime of 0 minus a number h, u of 0 equals 0, or u prime of 1 minus h, capital H, u of 1 equals 0. So this is a combination of these two cases. But here, the number that goes with the derivative is 1. And for these conditions, the operator has compact resolvent and the spectrum is again discrete for any of these conditions. Some of the positive results with the spectrum determines the potential. So this is a theorem given by Anbar-Sumian. I read about Anbar-Sumian, and he was an astrophysicist, and he published this paper in 1929, but it got the attention of mathematicians several years later. So what he proved is that if the eigenvalues of this boundary value problem, so here we have the Schrödinger operator with a potential, and here we have Neumann boundary conditions. So if the eigenvalues are the same as the boundary value problem for the potential 0, then we have that this potential has to be 0. And there are some generalizations of this result by Harel for compact symmetric space, by Davis for compact manifolds with boundary, and also for Neumann boundary conditions. So the Neumann boundary conditions is here very important, and also for trees with finite number of edges.
May I ask a question?
Yes.
You said that there are examples where it's not the case, where it's not where isospectrality does not imply equality for the potential. Yes. What are the simple examples for this?
Well, I will talk. I will talk later about it, but let me tell you, it could be well, one easy example when one can see that is when one has different boundary conditions and the same. No, okay. So maybe I don't have for you an example. I will have an example, but not now. Okay. But the point is that, so, well, I did try to construct an example, but I have not finished that yet. But it's when one has, so I will come back to that, you know, like, for example, one can have here an even potential, but then one has a not even perturbation, let's say, another potential that is not even. I will get back to that because that's one of the questions where the. Okay, so here is, I am now with the positive result. So there is this theorem by Borg where he considers, so here we have rho boundary conditions, and then we have a mixed boundary conditions. So rho at 0 and Dirichlet at 1. And then if I have the set of eigenvalues of this problem and of the other problem, then they determine the potentials and the constants. So H, the constant H, yeah, of the Rho boundary conditions. And there are other results that are similar to this. So, as we just said, it's well known that there are isospectral potentials, but they have to be, first of all, with Dirichlet boundary conditions. And so before I go to talk about this, this set of isospectral potentials with Dirichlet boundary conditions, I want to mention this compactness of isospectral potentials. That, well, there are three that I distinguish like three main results. So we have a closed Riemannian manifold, dimension n, and then we have the Laplacian, and we have a potential, and we have the set of isospectral potentials. So what Brüning proved in 1984 was that if we have this number, that is the infimum of all the integers that are bigger than n over 2, we have that if this set is bounded in, so this will be the H space we had before, that is W n 3 n naught minus 2 of m, then it's compact in the Smith topology. So this is a part of the condition. If this is bounded, then this is the case. And then he proved that for dimensions smaller than 3, this condition is satisfied. And then they have this, that the set of isospectral potentials is compact in the Smith topology of the manifold. And then later, Donnelly proved an extension of this, also the condition here is that this set is bounded in the solar space with S bigger than n over 2 minus 2. Then it's compact in the smooth topology of the potentials. And so this is an increasement. So he increased here to n smaller than or equal to 9. And this is positive isospectral. Then the set of non-negative potentials isospectral to be, yes, exactly, is compact in the smooth topology. So both of these results, they use that the isospectral, isospectral potentials would have the same heat invariance. And they use an asymptotic expansion of the heat kernels and the Sobolev embedding. So this is the same idea as there was before, but only for that part. And then there is another result I found by Shuli, Kaiser, Kian, and Sokorsi for a domain in Rn, bounded connected with the smooth boundary and the Dirichlet expression there. And this is a potential with a compact support in the domain. So here there is this condition that the set should be, this set is bounded in L infinity. So we have potentials that are also in L infinity in addition to be smooth. So when I have a set bounded in L infinity and I intersected it with the isospectral potentials to be, then this set is compact. So the intersection is compact in the Sobolev space HS for S smaller, strictly smaller than 2. So they do a lot of interesting work here, but they also use mostly the heat invariance and the short-time expansion of the heat traces and the heat kernels and Duhamel's principle to prove all this. So techniques are similar. Well, that's the idea. So for spectral stimuli operators with Dirichlet boundary conditions. So now we have this problem again. So for this part, I follow special Trubowitz, but it's based on several papers too. So we consider this operator, T sub Q, the operator associated to this eigenvalue problem with Dirichlet boundary conditions. And Q is a potential in L2. So these eigenvalues have an asymptotic expansion as n goes to infinity that has this form, which is also well known. So it's n squared by square plus this integral between 0 and 1 of the potential Q. And here we have the inner product of Q with the eigenfunctions of the potential 0, with the potential 0 of the Laplace operator only. And this is at a big O of 1 over n. So we will call this quantity that is important, the integral between 0 and 1 of Q of t, we call it C of Q. And then there is this sequence that is going to be Bn of Q, that is lambda n minus, so minus these two terms. So, lambda n minus n squared by square minus CQ. So this is a sequence, this B sub NQ is a sequence in L2. So with that in mind, so we associate now to the eigenvalue these quantities, C of Q and this sequence. So this decomposition leads to this diagram here. So for a potential associates the spectrum, and to a spectrum associates this number and the sequence in L2. So they analyze this map and the derivative. And with that, what they prove is this, analyzing this map, they prove that for a potential in L2, space P, the set of isospectral potentials to these potentials, this set forms a real analytic submanifold of L2 that lies in the hyperplane consisting of all functions that have the same value, whose integral or between 0 and 1 has the same value as the one of Q. And so this is a whole analytic submanifold of L2 And this set is unbounded in L2. So this set of isospectral potentials is very big. And so the part of the analysis is that they split. So they split the space L2 into this direct sum of even and uneven functions. And so here, this even and uneven is respect to the line 1/2, because we are interval 0, 1, so the 1/2 line. So there is a symmetry here. For even is q of 1 minus x should be equal to q of x, and the uneven is q of 1 minus x is equal to minus q of x. So splitting this, they prove that the restriction of the map is real analytic isomorphism on a neighborhood of 0 in this space of even functions. So an even function is uniquely determined by its spectrum, but there are isospectral potentials to a given to an even potential, but they are not even. So if we have this condition of being even, then is the spectrum determines the potential. So okay, so that's for isospectral potentials. Now, what is quasi-isospectrality? So we consider again the Schrödinger operator TQ with Dirichlet boundary conditions that I have here. This one is Schrödinger operator on the interval. And we define that two potentials are quasi-isospectral if the spectral of the corresponding operators are the same, with the exception of only one eigenvalue that is allowed to vary in a prescribed interval. So, of course, this definition applies also for any manifold and the potentials, or it doesn't have to be on an interval or with Dirichlet boundary conditions. So, I can also have a closed manifold. So the question here is, again, do quasi-isospectral potentials exist, and how will be this set of quasi-isospectral potentials? So this is, of course, related to and also a very old problem of inserting eigenvalues for operator was studied in a half line or in a line, so in R or in 0 infinity. And so, as I said, this has a long history and has also several applications, as I also found out, to inverse scattering, supersymmetric quantum mechanics, then comparison theorems, and also to solutions of the KDB hierarchy. So that was why it was also so much studied. So these are methods to insert. So if I have an Sturm-Liouville operator and want to insert an eigenvalue or remove an eigenvalue, but it has to be in a spectral gap. So the single commutator method serves for this, and it was first goes back to Jacobi, Darboux, Krum, Schmicke, Dijk. But this method, this single commutator method, has limitations, and the limitations I will show later is that introduces singularities in the eigenfunctions and in the potential. So if one doesn't want to introduce singularities, one has to restrict to strictly positive eigenfunctions, and that's, as we know, is not always possible. And then there is so this is the single commutator method, and then there is the double commutation method, commutator. And this was also introduced by Genfal and Levitan in 1955. And then it was, the method was improved by Ketsetsi and Telch. So this allows to insert eigenvalues in any spectral gap. And they rely on a factorization of the operator that includes an eigenfunction and an eigenvalue. And another method, besides this single commutator and double commutator method, but that uses in the proof the same idea, is to use a lemma by Darboux. And this Darboux lemma is here the following. So I will explain. So this lemma by Darboux fixes two eigenvalues and has a not trivial solution of the eigenvalue equation with one of the eigenvalues, and F is a non-trivial solution, and G is another non-trivial solution with the other eigenvalue. So we have here two eigenfunctions with the corresponding eigenvalues, and then defines this function H, that is 1 over G times the Wronskian of the two eigenfunctions. So Gf prime minus G prime F. And this function is a non-trivial solution to this Schrödinger operator, but here the potential has changed. The potential is now the whole potential, but it takes off twice the second derivative of log of the eigenfunction G. And then this function H is a eigenfunction of this problem with the first eigenvalue. So it changes an eigenfunction. So this is the same eigenvalue here, so lambda u, but this is another potential. The problem is, as you know, if G vanishes, so here we have singularities that are not in L2, and here we also have singularities. So it messes up everything. So this is not so great. Well, and in the case when these eigenvalues are the same, the general solution of this equation is given by this expression, 1 over Ga plus B integral between 0 and x, G squared of x. And this is for any A in R. So this is this lemma that, of course, is very useful, but it has the problem. However, when one applies this lemma twice, applying twice this lemma solves many problems if one applies in a good way. So what Bilota, Morazzi, and Turco made in a paper they have about isospectrality, quasi-isospectrality, is that well, they construct potentials P and Q that are quasi-isospectral, but they change only one eigenvalue that is allowed to change in a prescribed way. They indeed construct a family, a continuous family of these operators here. And so they change only one eigenvalue, but the eigenfunctions change. So, and then what they do is to apply twice this lemma by Darboux. And so the corresponding eigenfunctions here are these ones written here. So from here, I am not saying who is this W of NT, this beta of NT. These are some solutions of some problem where one considers this eigenvalue and using a shooting method. And one is Wronskian and one is some solutions to some boundary value problem. But the point is, and some combinations of solutions too. So this construction is elaborate, so I don't go into the details here. But the point is that, so okay, here CM are eigenfunctions corresponding to these eigenvalues. These functions are going to be smooth. They are not going to have singularities in this one here. So they are well defined. So that is good. And then we have another potential that is different to the initial potential. And then they are quasi-isospectral. Okay, so now I have here an example of this string Liouville problem. So one has here, this is just a constant. So one has minus 2 derivatives plus the constant plus the function equal to lambda y for this eigenvalue problem. But here we have boundary conditions, and we just let these functions a of t and b of t be functions of a parameter t. And they are smooth depending on this parameter, and we require that b is different from 0. So for these different boundary conditions, we have that these operators are isospectral for any fixed t, or quite they are quasi-isospectral. No, they are isospectral. And so this example is very similar to the initial question that Strum and Liouville had back in 1836, and then in there they have papers appearing at the same time when they consider solutions to this problem where it was possible. And just a simple example, but different boundary conditions. So what we can say so far about quasi-isospectral potentials is if we have a closed Riemann manifold of dimension n, and we have the Laplace-Beltrami operator and the potential. So we know that there is this asymptotic expansion of the heat trace. And what we have is that if we have quasi-isospectral potentials, where we change the kth eigenvalue, that is not the first eigenvalue, it's a different eigenvalue. So we change this eigenvalue, then the heat invariance for the potentials are the same for j smaller than 1 plus n over 2. So n is the dimension of n. And for that, so we have to see is simple. We have to see that the operators, so these operators are trace class, like these operators are trace class. For the potentials, they have expansions. So the trace of the difference also has an expansion, and at the end, so here this t is smaller than 0 because this is true. But for t small, one can just bound this difference, this trace, the trace of this difference by big O of t. But here we also have the difference of the eigenvalues. So if these two are close, so this is also also close. But also we have t here corresponding. That's the idea there. And also, if of course one will ask, or I have the question still, where one could prove that the asymptote, that all the heat invariants are the same, and that's something I don't know yet, so I have not figured it out. Could be, it could not be. The point is that these potentials could be very far in L2 norm. So, and for Sturm-Liouville operators with Dirichlet boundary conditions. So we know by results of Kilke, Buñuelo-Sabajeto, that we have this asymptotic expansion of the heat trace. So here we have the trace of the operator, and so here this term is the same. It doesn't depend on the potential, but this term here depends on the potential by the integral. Here we have the values at the boundary of the potential, and here we have more values. But from what we can have of this of the previous theorem is that for these Sturm-Liouville operators on the interval with Dirichlet boundary conditions, if they are quasi-isospectral, then the integrals between 0 and 1 of the potentials are the same. And I just remind you, this is also the term that appears in the constant term, the asymptotic expansion of the eigenvalues. And these statements remain true also if we perturb only finitely many eigenvalues instead of only one. And this is all what I wanted to tell you. Thank you very much for.
Thank you very much. We can thank the speaker for the great talk. We have time for a few questions. Don't hesitate to unmute yourself.
I have a question. So is there any hope for these type of methods to be able to be lifted to the situation of manifolds rather than potentials? For example, distance between metrics and the appropriate Sobolev spaces. And,
well, yes, I think that's something I would like to investigate too. Mm-hmm. So where one can extend these to some cases and to manifolds instead of intervals. Mm-hmm. And I think like one will have to generalize these the methods or the lemma, this lemma by Darboux or some of these methods.
Mhm.
So, well, one could start maybe by roads or something, and I don't know now how to do
Okay.
it.
Mhm. Maybe rotationally invariant metrics could be a good starting, because then you can have some sort of one-dimensional family to apply the Darboux lemma.
Yes,
Clara, I have a question.
that
So,
would be a good idea. Yes.
this is Dima. If you have not one different eigenvalue, not one different eigenvalue, but 2 or 3 or something, how will things change?
They don't change. One can apply it. It's the same. If one has finitely many, yes, one can apply the same method. Yes.
And do you know what happens on trees? You were mentioning some results.
Yes, so on trees, I only know. Well, I will go back again to this. And on trees, I don't know exactly what happens. I just know this result here by where was it? By Davis. He considered
Okay.
trees also in this paper. This paper is nice because it's very general. He requires a very general setting and tries to do it like in a metric space with some function like a hit kernel with a function that has the hit kernel type.
And because for graphs, there is this result that if you have like 2 bridges in the graph, so if you disconnect the graph, I think if you have a graph connected to a graph by 2 edges, if you clip the connection points, then the graphs are Laplacians are isospectral, but I'm not sure about potentials. Something like that. I mean, I forgot exactly how it
Yeah,
works.
I think then maybe you will have to have these periodicity conditions. Thank you.
Thank you, Dina, for the question. I was myself wondering, so in the first examples you gave with the domains, the isospectral domains, well, at the beginning of the talk, there's a finite number of isospectral domains, and then it looks like in the following, you always have continuums and things like that. Is there other settings where you can have, well, sorry, so there's 2 questions. Do you always have a continuum of isospectral domains or potentials in the examples you construct? And also, do you have conditions which make things discrete?
So, okay, let me understand better the question. So you are asking if what happens if one has only a smooth potentials?
No, so it looks like you're managing, well, you're saying that the space of isospectral potentials, for instance, is compact. I mean, if I'm not wrong.
Yes, so that, well, I will, yeah, exactly. So here are these results of isospectral potentials of,
for instance, yeah.
Brunin and Donnelly. Yes, so they consider here only a smooth.
No, so what I found interesting is that in the first example of the construction by Caroline Gordon and etc., it's really relying on the fact that they reorganize things, and in a sense you feel like there can only be a discrete amount of possibilities or a finite amount of possibilities to reorganize the pieces to make isospectral things. And that's clear that you're never going to get a continuum of isospectral domains this way, while it looks like the constructions we see later in the talks are more continuous. So is there something about that? Do you have, I'm sorry, it's a vague question.
No, I think I understand. Well, like, of course, one would like to know if this set will be finite. And well, is not clear. Like for surfaces with negative constant curvature, there is finiteness.
Okay, and is there finiteness in
This
other
is finiteness,
settings?
and then here is finiteness for hyperbolic surfaces of finite area. So, but that that uses some other methods. So one thing what we like to know is where there are only finitely many, and know if someone knows if there are more cases. If there are more cases where there is only finiteness.
So is there an example where it's not finite, where there's an infinite number of isospectral?
Like for these potentials, I find this theorem very interesting, the one of Peschel-Trubowitz, because that really shows not at all finiteness. And then what they have also in the other theorem is that in the Schully and the others is that they need to bound to have a bounded set. You know? So they have to restrict so to not to have too many. And I think there's really many cases.
Okay, thank you very much. Does anyone else have a question?
Clara, I seem to remember there were some results by Brooks, Perry, and Peterson in dimension 3.
Yes. Yes.
You remember what they were? I forgot. I mean, what the hell exactly?
I think so. They have something about for higher dimensions. I'm not totally sure at this moment, but they do have that the scattering phase or the resonances. I think a scattering phase in dimension 3 that will determine the topological and the geometric type of the space up to finitely many options, if I remember correctly.
Okay, well, I think now is a good time to thank the speaker again. So thank you, Clara.
Thank you very much for the invitation. Okay.
And
thank you, Clara.
Next time we meet again. So we meet again next week with a talk by Marco Michetti, who's going to tell us about the maximization of Neumann eigenvalues and the diameter constraints. So thank you very much and have a nice week.
Thanks a lot, Clara, for the talk.